on my computer. Okay. All right, now we're up and running. Okay. So let's see, just some announcements and some other things about what's going on for the next couple weeks. Let's see, first of all, and do I have my notes that I wanted to grab for today's lecture? Okay, they're here. Okay, so for the upcoming schedule, let me see if I can log into Blackboard. Someone just said there's an issue with it. So it might not let me, yeah, I haven't updated anything in Blackboard. Okay. Let me, well, I'll just talk about it. Okay. So the experiment we're doing, let me see if I even have, no, I didn't update the web page at all. Sorry. It's been a busy morning. The experiment we're doing is the Frito-Crafts acylation. So we'll write that out here. The reaction is called Frito-Crafts acylation, and we're doing on a substrate called ferrocene. So we'll talk today about what all that means and get us ready for the next 2 weeks. So so today we're just doing kind of a little orientation. Next Wednesday is the holiday, so we won't have any meeting at all. And then 2 weeks from today, which is the 18th, if I have my date right, does that sound about right? I just pulled that out of nowhere, yeah. So the 18th is when we're going to have a synchronous meeting, and we're going to watch the video of the procedure together. So, so hopefully you can join for that for the live show, because we're going to have a discussion. I'm going to pause at several points, and we're going to ask questions and answer questions, and have a chance to kind of figure out what we're doing and why we're doing it. And then there's actually questions embedded in the video. This is a video that I made myself back in March when the world went sideways. So we're gonna, every time there's a question, we're gonna pause it, and we're either going to discuss it right then and there, or I'm gonna say, okay, note this question. This is gonna be part of your lab report. And so there's these 20 questions or whatever, 15 questions are gonna be part of the lab report. And we're going to encounter them throughout. So you don't have to write them down. I have a handout that already has all the questions on there. So before that, before we have that synchronous meeting where we're watching the video, 2 weeks from today, that's when you have to take the do the TLC. There's a TLC. Oops, sorry. I'll mute everyone just to make sure we're all good. There we go. Within the next 2 weeks, we're going to have, we're going to dig into the thin layer chromatography procedure and technique, make sure we know that very well. So I have a Blackboard quiz that will be that is set up and ready to go. So you can take that whenever you want. I have it with the same format we've had the other ones, where you can repeat it as many times as you want and, work to improve your grade, and more importantly to, learn the technique and understand what's going on, so that when we see those questions down the road, we'll have some confidence answering them. I also have a TLC simulator, which lets you take 2 TLC plates side by side, and you can vary the solvents, and then you can develop them, simultaneously, and you can see the effect that different solvents have on the RF. So that's another really important concept that most students, after the whole year of organic chem lab, still don't quite have it right. So I created a simulator where you could just kind of go through lots of different examples and try it, and until you know what's going on. And I have a worksheet that accompanies the TLC simulator to kind of guide you through step by step some things to try and some things to observe. Okay, so reviewing TLC and taking the quiz are 2 of the important things that you're going to be doing for that run through that we're going to do of the video. And then preparing your notebook. So we're going to be doing this is our last notebook exercise, because our very last experiment that we're doing is the isolation of eugenol from cloves. And that is natural product isolation. It doesn't have moles and, you know, reagents and equivalents and calculations and their theoretical yield and all that kind of stuff. It doesn't have that kind of aspect to it. So we're not going to have like, this is our last reagent table that we're going to have to make. So did I just hear like 3 cheers? I probably heard some cheering there when, when you said finally we're done with our reagent tables. So one last notebook to prepare. The procedure is posted. And what I'll do is I'll spend some time updating the course homepage too, so that you can find it in either place in case Blackboard goes down like it might be right now. So during the procedure, as we're watching it together, I think it's only like maybe 30 minutes that we'll be going through it, maybe 45 because we're going to be stopping and pausing. But you're going to be recording observations. So you don't, we're all going to do that synchronously. And so then at the end of the day, you know, you'll have the following week to finish up answering the questions, you know, and you'll be submitting that with your notebook. So kind of like we did with the Aldol, but the difference is we're going to be meeting synchronously so we can discuss these embedded questions as they go along. So does that sound like a plan? Any questions about what's coming up the next couple of weeks? All right. You know where to find me if questions come up. And sorry if Blackboard is down right now and you're hoping to get some stuff done today, because like Wednesdays are my day to get my lab done, but we do have the holiday next week, so we have a little extra time this week to get this done. Okay, so what I want to talk about, oh, I'm sorry, and there's one other major technique that we're doing, because we've all done TLC before and we're hopefully, you know, somewhat familiar with that technique. But the other major technique that we're doing is called column chromatography. And so that is just, it uses the same theory as TLC. TLC stands for thin layer chromatography, where you have a thin layer of silica gel stuck to a plate. And column chromatography takes an entire glass column with the silica gel, and you pass your samples through there, and same thing, your spots separate, and it's a way to actually separate a mixture and collect, you know, component A, component B, component C, where TLC is typically just an analytical tool. You analyze just a microscopic sample of your reaction mixture or whatever, and you analyze it, say, oh, I have 2 things in my mixture or 3 things in my mixture, or oh, there's still starting material left, or that sort of thing. So we take it from that analytical tool and we scale it up to do something where we can actually purify. We have a mixture, we've finished our reaction, we have some unreacted starting material in there, or maybe we have a byproduct in there or something else. So we can run a column and purify our compound from any other impurities. Or maybe if we have 2 products, we might be able to isolate both products pure. So we've talked about techniques like distillation and recrystallization and those sorts of things, and those are all well and fine, but they really only apply in certain circumstances. And even when you do a recrystallization, you throw out a significant amount of your product because, you know, it still has some solubility in the solvent that you're using. So you have to sacrifice some of your product in order to get the majority of it pure. When you do a column, you now, you know, 100% of your product goes in, 100% of your product comes out. And so it's a very efficient way to isolate your compound, and it could be a solid or a liquid, you know, or an oil. It doesn't matter what kind of compound you have. It will be something that you can purify through column chromatography. So I'm part of the procedure, part of the work, part of the preparation is to ask you to explore that technique. So there's, you know, the Nichols book has great pictures and that sort of thing. I don't know if I provided any more links. I might provide some other resources if I can find them. But so I want you to get familiarized with the technique. I want you to write out a procedure as part of your procedure in your notebook. Not only are we doing the Frito-Crafts reaction, but at the end, we're purifying our product by column chromatography. So I want you to go through, have that already in your notebook, and then we'll be taking observations all during our meeting. So that's another cool thing about that I really love about this experiment, is that we're having a chance to do chromatography on it. I think you guys actually did. I think once we revised the 3140, I apologize because I actually haven't taught the first semester lab ever since we moved to semesters. I think there's a chromatography experiment in 3140. Maybe it's the spearmint oil. Does that sound right? Did you guys get to do that hands-on in the spring? Does that sound familiar? Where you did like a drop, you might have done like a tiny test tube version of it, tiny. No one sounds familiar. Oh my gosh. Okay. So I'll have to follow up about that because I thought they added that into the 3140, or maybe it was later in the semester and we lost it when we went online. But good. Well, that makes it even more important that we're doing it today because it's such a critical technique. Seriously, when we're in lab, when you're doing organic synthesis and you're in an organic lab, you do a column, like you do a reaction and then you run a column. And you do another reaction, you run another column. You run columns every day, all day, every day. So it's such a critical skill to learn about and theory to understand. And it ties exactly with TLC. So as you explore and learn TLC, you're gonna be able to understand and answer questions about column chromatography. So what's very cool about this particular reaction is ferrocene is a colored compound. It's yellow. It's a yellow powder. And the product, acylferrocene, is also a colored compound. It's more like an orange. It's slightly different color, but it's still colored. And the byproduct, we might get some diacylferrocene. That's also a colored product. So what's very cool is as your compounds are traveling through the column, you can actually see visually where they are as they make their progress through the column. Where normally, like you imagine a TLC plate, usually everything's colorless and you spot the TLC and you develop the TLC and then you take it out and it looks the same as before and after, right? And we have to do something to visualize our spots, right? So that's the case with most columns, but in this reaction, our products are colored and we can actually see them as we're collecting them. So it makes for a very, so soon as COVID happened, I knew I had to get in the lab and film this so that you guys would still be able to experience it. It's one of my favorite labs. So, okay, so what is a Friedel-Crafts acylation? It's an example of a reaction called the electrophilic aromatic substitution. A lot of words there. A lot of times I abbreviate this reaction as EAS, electrophilic aromatic substitution. For some reason, that abbreviation has never like taken off. Like, you know, we have SN2 and SN1 and all these other cool names. I have no idea why this is not abbreviated. But anyway, those of you who are taking 3150 right now with me, this is in chapter 18. We are going to be, working on problems for this reaction tomorrow. So you're going to be seeing this right away. You're getting a little sneak peek here, and that will prepare you a little better for what you'll see in lecture. So the general reaction is we take benzene or some benzene derivative or any other aromatic compound. We just talked about aromaticity as well. And you react it with some super duper electrophile, super reactive electrophile. And what happens is the electrophile ends up, actually I'll show you the mechanism. Let's draw the product and then we can look at the mechanism. The electrophile adds up adding to one of the positions on the benzene ring. And so, someone did say there was a little column chromatography in 3140. So that's good. So might have been a little different instructor to instructor or semester to semester, depending on when you had it or if there's a holiday or something like that. But that's good. Hopefully for some of you, this will be your second exposure to it. So what happened? Well, we had a hydrogen here, right, in benzene, and we replaced that hydrogen with some electrophilic group. And so it's described as a substitution reaction, right, because you replace a hydrogen, but we replaced it with an electrophile. And so the mechanism is just a two-step mechanism. After we have some super hot electrophile, what happens is the benzene ring acts as a nucleophile and one of the pi bonds of the benzene ring attacks. So if we add the electrophile, let's say to that top right carbon where we wanted to put it. Now what happens is we broke that pi bond and it went out and attacked the electrophile. So this carbon here ends up now with a positive charge. It just lost a bond and now it has only 3 bonds. Okay, so so that is our first step in the reaction, is adding the electrophile. And then the second step of the reaction is we have some kind of base, any base at all can come in here and remove that proton. And that will give us back the pi bond and give us back our benzene ring. So remember, what's very, very special about benzene or any other aromatic compound is that it has those conjugated pi bonds within a cyclic system. And so the tricky part of this mechanism is right here. This part is very, very slow and difficult because we sacrifice aromaticity to add the electrophile. So big uphill step initially. But then in the second step, when we lose a proton, it is very fast and easy because we get our aromatic ring back. So overall, the key is that in these substitution reactions, our aromaticity, our aromatic ring never gets lost permanently. And that's why this makes it an okay reaction for the aromatic ring to undergo, because it will, it's starts out very stable and ends up very stable. So this is called electrophilic aromatic substitution. Where this gets really interesting is when we do, if you have a substituent on the initial ring, right? So if you had a methyl group here, you know, or a nitro group or a chlorine here and so on, now we have to think about, well, where is the incoming electrophile going to go? Is it going to go ortho to the existing substituent, or meta or para, right? What if we have 2 substituents? How do we decide where to put the incoming groups? So that's the stuff that we're going to be exploring in chapter 18, along with, well, what are the electrophiles that we're going to add? So the reaction we're doing here is called an acylation reaction, the Friedel-Crafts acylation reaction. Normally what that looks like is we will add a acid chloride and aluminum trichloride. So those will be our reaction conditions for a typical Friedel-Crafts acylation. And what happens is the aluminum trichloride kind of grabs that chlorine atom and rips it off. and we end up getting an acylium ion. I'll show you the mechanism in just a minute. What we're going to end up adding, the electrophile we're going to end up adding, is an acyl group. I'll show you the mechanism in just a second here, just so we have a complete picture. So we call this an acylation reaction. Remember, an acyl group means it's a carbonyl. We called reactions with esters, we called those acyl substitution reactions because they were happening at a carbonyl. So when you add an acyl group onto a benzene ring, it's called a Friedel-Crafts acylation reaction. And what happens here, the electrophile, when these two come together and you pull off the chlorine leaving group, the chloride leaving group kind of gets ripped off by the aluminum trichloride, you get this resonance stabilized carbanion. Now, we've never seen a carbocation like that, right? That's really weird to have it on a carbonyl. That is actually super weird. The only place we've seen something like that is maybe in mass spec, when we looked at some of the fragmentation that we can have. But this is actually resonance stabilized. This is called the acylium ion. It's called an acylium ion, and this is the electrophile, the E+ group, that we would add in this first step. So so that's called the Friedel-Crafts acylation, and it's a way to make an aromatic ketone, Okay, so what is the reaction we're doing? Because we're not doing Friedel-Crafts acylation of benzene. We're doing Friedel-Crafts acylation of ferrocene. So let's see what ferrocene looks like. The way we draw ferrocene is like this. We have an iron metal, an iron 2 metal, and it is sandwiched by two aromatic rings. It's a 5-membered ring that's aromatic, and it looks like this, which is super weird, right? So welcome to the world of organometallic complexes, transition metal complexes, where you have ligands that are associated with a metal. Okay, so what is this ring? This is called the cyclopentadienyl anion. The cyclopentadienyl anion. And actually, we looked at this anion just yesterday. If you were with me for the problem-solving session, if you take cyclopentadiene, and you treat it with a strong base, some very strong base, it can deprotonate the carbon. It can deprotonate the carbon. We can, there's still one hydrogen there, so we could just double check our formal charge math, right? If you deprotonate, now you have a lone pair here. So we have 1, 2, 3, 4, 5 for our formal charge count, and carbon only wants 4. So we make this carbanion, and this carbanion is highly resonance stabilized. Highly resonance stabilized, and it's so resonance stabilized you could actually put the negative charge on every single carbon atom. Not only is it resonance stabilized, but we have a cyclic system, and we have a p orbital on every single carbon, and we have how many electrons in those p orbitals? 2, 4, 6 electrons in those p orbitals. What do all those ingredients add up to? What do all those ingredients add up to when you have 6 electrons in p orbitals and it's cyclic? That all adds up to aromaticity. This is aromatic. So it is aromatic like benzene, and therefore it can do electrophilic aromatic substitution reactions with the same mechanism we had, analogous mechanism we had with benzene. So a way that the cyclopentadienyl anion can be represented is just with a circle in the middle to represent those delocalized electrons, and a minus in the middle to represent the charge. It's a charged structure as well, right? Have you seen, if you recall, benzene can be drawn, right, just with a circle in the middle instead of the 3 separate pi bonds. So that's how we draw the cyclopentadienyl anion. So if you take the cyclopentadienyl anion and mix it with iron 2+, then to get a neutral species, you would have 2 cyclopentadienyl rings, each with a -1 charge, to counteract the, to balance out the +2 charge, and it ends up being neutral, being a neutral complex. So this is a stable transition. It's described as a transition metal complex, and it's it is kind of cool because it's yellow, so it's something that is easier to work with because we can see it and it's a solid, unlike benzene, which is a liquid and is volatile and is also carcinogenic. So a lot of reasons it's nice to use ferrocene instead of benzene for this reaction. All right, so what we're going to be doing is we're going to be adding an acyl group to one of those. We're actually going to be adding a methyl keto group, and the actual acyl group, onto one of the cyclopentane rings, cyclopentadienyl rings, excuse me. So we just kind of draw this line here. I know this is kind of a weird way to represent it. We kind of draw a line to the center of the cyclopentadienyl anion because the iron is complexing with all 6 of those pi electrons. So you can kind of think of it as coordinating to all 5 carbon atoms, and that's what our ferrocene complex looks like. So we're going to get acylferrocene as our product, but we could also maybe diacylate with, so we could overreact the product and get two acyl groups. So we have a chance. So in the end, when we do our reaction, it's very ideal for doing a chromatographic purification, because we might have some unreacted ferrocene left over in our product mixture. We hopefully most of what we have is our product, but then we also might have some of this diacylated product. And so the goal of the chromatography is to separate all three of those and isolate our pure acylferrocene. Okay, and one last thing is, instead of the acid chloride, so what I said, typically the reaction conditions would be acetyl chloride and AlCl3. And that's how we would get our psyllium ion. But that's tough to do because acid chlorides, we talked about this a little bit with the nylon experiment, right? Acid chlorides are so reactive, so electrophilic, that they're very hard to handle. They're noxious, they're corrosive, they're all sorts of bad things. And AlCl3 is not such fun stuff to work with too. So the reaction conditions we have are better suited for the undergraduate laboratory. And what we're going to be using is, instead of acid chloride, we're going to use the anhydride. Remember, we just, again, reviewed the concept of reactivity of these different carboxylic acid derivatives. And this was the most reactive carboxylic acid derivative. And what was the second most? The anhydride was the second most reactive derivative. So instead of having the chloride leaving group, we're going to have an acetate leaving group. But it's a lot easier to handle, it's a lot easier to work with, and so on. And so we're gonna, and instead of using a Lewis acid, like aluminum trichloride, we're just using a Bronsted-Lowry acid, we're using phosphoric acid. So the phosphoric acid will help, like protonate this and make it a really good leaving group, and this facilitates the formation of the psyllium ion as well. So I just wanted to spend a little time today in introducing or reviewing, for some of you, the electrophilic aromatic substitution reaction, and the idea of doing an acylation reaction, what the structure of ferrocene looks like, because that's so weird, and just looking at recognizing it's just another example of an aromatic compound. And then also discussing the reaction conditions that you're going to find, the reagents that you'll find in the procedure that's posted is different than the ones we typically have in our textbook. So I wanted to make sure you see that as the parallel between those, as it's just an alternate way to make an psyllium ion. Okay, so that's kind of all I wanted to talk about today. Are there any questions about what's coming up the next couple of weeks? And hopefully Blackboard's up and running again soon, if not already, so that you can see the detail. And I know I broke it up as terms of before lab and during lab and after lab, but the during lab part is when we're meeting synchronously 2 weeks from now. So you, all the stuff that was listed in that, before lab, you have 2 weeks to get that done. I would like all that done though before we have our synchronous meeting, so that you'll be able to answer the questions that we're discussing as we go through the experiment, right? You need to have that background work done so that you're ready to work. This time it's not a safety issue. I'm quite certain no one's gonna blow something up in a Zoom environment, but in terms of a mentally ready and able to answer questions and know what you're doing and why, that's why we're going to do that work ahead of time to make sure we're prepared for the experiment that we're going to be doing virtually. Yeah, there could be some explosions. I guess everything's possible, but this is definitely a much safer. No PPE is needed. You're good. You could just show up and watch out for static electricity charges, I guess. Um, let's see. I graded your your NMR homework. I wanted to make sure you got some feedback. Oh, I did want to do another NMR homework. We don't have to do that right away. So I might assign that for the second week to give you time to do that, because you have plenty to keep you busy in the next couple of weeks. So that'll be good. And questions, swipe back for the first page. So yeah, here's our Frito Crafts acylation of ferrocene. Any other questions? We feel like we know what we're doing moving forward. All right, well, email me if you have any questions along the way. And I'll make sure I have everything set up in Gradescope. You guys keep me on my toes and remind me every time something's missing. So, but the Blackboard quiz is already ready to go. So if you want to start working on that today, knock yourself out. That would be great. All right, so I will stop the recording, but you're free to stick around and ask questions if you still have questions.